Okay, let's talk about matrices, vectors, and scalars. So if you've taken linear algebra, then this is 100% review. Okay, 99% review, because linear algebra typically does not cover traces. And if you've taken Calc 3, which I believe all of you probably have by now, you will also recognize things like vectors, because we talk about multidimensional spaces, and therefore vectors is how we describe those elements. So we want to make sure that we're aware of the basics of a matrix, how it's composed, some basic operations on the matrix, a vector and a definition, what that means, and scalars and how they interact with matrices and vectors. So let's dive into some of these basics. If this particular section interests you, then you have not taken linear algebra, then I highly recommend linear algebra, as it is all about matrices and eigenvectors and values. Okay. So definition of a matrix is a rectangular array of numbers, usually enclosed by brackets. Generally, we use uppercase letters to represent matrices. So for example, we can label this matrix matrix A, and it is a 2 by 3 matrix, okay? So you're always going to count how many rows you have. So there are 2 rows, and then the second dimension will always be the column. So we have 1, 2, 3 columns. So that makes it a 2 by 3 matrix. Okay, a vector is just a matrix, but specifically with just one column or one row. So we can have column vectors or we can have row vectors. So that's one thing I forgot to put in here, was what a row vector would look like. Let me actually put it inside here. Or b is equal to -1. We don't usually use commas when we are talking about vectors. It's more spacing. So this is a vector. This is a column vector because everything's in one column. This is considered a row vector because everything's in one row. But vectors do not have multiple columns or multiple rows. So a column vector will not have multiple columns. It only have a single column, and it can have as many rows or elements in the column. And a row vector won't have multiple rows, but it will have multiple columns, as each column represents an element in the vector. So a scalar is a 1 by 1 matrix that is just a single number. So a scalar is another name for like a constant when we were talking about algebra class, and there was that +5 at the end of the equation. Well, we knew that that was just a constant. There's no variables involved, and that's exactly what we are referencing when we're talking about a scalar. It is just a number. A real number, by the way. So the only thing that scalar is not usually is an imaginary number. Now, some matrix algebra that we need to brush up on and just make sure we know how, well, I shouldn't really say brush up on, because some of you may not have any matrix backgrounds, and that's fine. When we're adding 2 matrices, they have to be exactly the same size. So again, this is a 2 by 3. So we can only add another 2 by 3 matrix, because how we would add matrices is element-wise. So see how this is the first row, first column element? Then we would add that to first row, first column element here, giving us 1 + 4 as our new first row, first column element, and that gives us 5. So here's our resulting 2 by 3 matrix. So matrix addition or subtraction, because subtraction is just adding a negative, are both going to have to be picking matrices that are exactly the same size. And it is, the operation is undefined. If you are trying to add a 2 by 3 with a 4 by 8, you would just say undefined, because those cannot be added together. When we want to multiply by a scalar, we just multiply each element by that scalar. So very similar to what you would do if you were multiplying a linear equation by 3, you know that you have to distribute and multiply every single term, including the other side of the equal sign, by that 3. So the same is true when we are multiplying that in a matrix. We want to make sure we multiply every element by the scalar and giving us our new output. Again, same size though. The size does not change when multiplying by a scalar. So matrix multiplication is the more complicated one. So when you are multiplying matrices, they don't necessarily need to be exactly the same size. There's other criteria we need to meet. So if you look, if a matrix is generically m by n, then the only way you can multiply another matrix with it is if it starts with the same number of columns that the first one has, must be the same number of rows that the second one has. So notice that m, the number of rows of the first one, and p, the number of columns of the second one, they do not need to be the same. Only the inner values need to be the same. And you'll also notice that the resulting size of the matrix, the product matrix, will be the size of the outer dimensions, an m by p matrix. So for example, if we take a look at this one here, let me show you how we would do matrix multiplication. So the first thing we want to recognize when we're working with a multiplication problem is the dimensions, to make sure that this is a defined operation. Remember, if the inner dimensions do not match, then we would say undefined. We cannot compute. So we have 2 rows and 3 columns. So this is a 2 by 3 matrix. And this one here has 3 rows and 2 columns, making it a 3 by 2 matrix. So I'm verifying that the inner dimensions are the same, which means that matrix multiplication is allowed. And I'm also going to recognize that when I multiply these matrices, I am going to result in a 2 by 2 matrix. Okay, so now I know I'm looking for a 2 by 2 matrix, so my output is going to be a square matrix with 4 entries, 2 rows and 2 columns. So I'll do these little underlines to show you that these are the 4 entries we need to calculate. And the way that we are going to apply multiplication is by multiplying row by column. So this first calculation is going to be row 1 times column 1. Now, this first matrix is going to be the rows. So we are always going to be looking at the rows of the first and the columns of the second matrix. So the order in which you multiply does matter. Note down here where I state that matrix multiplication is not commutative. So just because I can multiply this from left to right does not mean I can flip it around and multiply the second matrix times the first matrix. Although in this case, the outer dimensions happen to match as well, so I would be able to perform the multiplication both ways, but it does not give me the same answer. When I multiply, if I switch the order of these 2 matrices, I wouldn't be producing a 2 by 2, I would be producing a 3 by 3 matrix. Okay, so row 1 is this row here, 1, 2, -1. So I'm going to copy that down. And column 1 is here, 2, 3, 7. So what we are going to do is we are going to multiply element-wise and then add them all up. Okay, essentially what we are doing if you do take linear algebra is we are performing a dot product between these vectors that have exactly the same elements in them, same number of elements. They each have 3 elements. So I get 1 times 2 is 2, 2 times 3 is 6, and -1 times 7 is -7. add these together, and we get positive 1 as our entry. Is a positive 1 as our entry for first row. So this is row 1, column 1 is going to be a 1. So now we need row 1, column 2. Okay, well, row 1 is still the same thing, 1, 2, negative 1. But column 2 is here. So we're going to use 0, negative 2, 0. Multiply straight across. And we get 1 times 0 is 0. 2 times negative 2 is negative 4. Negative 1 times 0 is 0. Add it all up. Our row 1, column 2 element is going to be negative 4. Okay, so now we have exhausted row 1 because we've multiplied it by all the columns in the second matrix. So now we are moving on to row 2, column 1. So here is row 2, 0, 4, 2, and column 1 is the 2, 3, 7. So we get 0 times 2 is 0, 4 times 3 is 12, and 2 times 7 is 14, giving us our row 2, column 2 element. Row 2, column 1 element to be 28. And then we are going to do row 2, column 2. Let me make some room for that. So I'm erasing the row 1 stuff. Okay. So our row 2 again is 0, 4, 2. Column 2 is 0, negative 2, 0. 0 times 0 is 0. 4 times negative 2 is negative 8. And 2 times 0 is 0, giving us our row 2, column 2 element to be negative 8. So this 2 by 2 matrix is our product result. Now, matrix multiplication can be done on your calculator. Whether you have an 84, 83, 84, or 89, you can put matrices in and multiply them on the calculator. I am unable to show you the calculator one because my 89 does not currently turn on. And my 83 and my 83, 84, I'm not even sure if any of you guys have 83s or 84s. So I will post in the course some videos showing how to do this kind of stuff in your calculator so that you don't have to try to figure that out on your own. Now, special matrices, the zero matrix identify the identity of addition. So when we are talking about identities in math, we are talking about things that apply an operation but don't change anything. So when we're referring to the identity of addition, we're saying what number, when added to another, doesn't actually change the number. And we know that that is 0. So the zero matrix, which is when all the elements in the matrix are zeros, is our identity matrix for addition. So another thing that you guys should have seen as notation is what space we're in, especially if you've taken Calc 3 or linear algebra, and we denote it by this fancy R stands for the real numbers, because again, we are not exploring imaginary numbers. And this 2, R2, means a two-dimensional space, which is all the linear lines that you've particularly worked with in elementary algebra, intermediate algebra course with X's and Y's. Now, when you have a 3 by 3 matrix, this is a matrix that is talking about vectors in R3 or a three-dimensional space. So that would be an X, Y, Z type axis. And these are not infinite spaces, but we can go to what we call our n, where n represents any number, any integer. So we can have very large multidimensional spaces. Oh, I was talking about the spaces, but I forgot to talk about this last identity. So the identity of multiplication, as you know, when you multiply by 1, it does not change anything. when we are doing basic multiplication in the idea of matrix multiplication, the 1 is the important part, but the 1s aren't everywhere. The 1s are just on this diagonal here, the top left to the bottom right diagonal. Now, trace and determinant. So a determinant and the trace are defined for square matrices. Okay, so we're talking about n by n, meaning 2 by 2, 3 by 3, 4 by 4. The trace of a square matrix is defined to be the sum of the diagonal elements. Okay, so again, we were talking about that identity. That left diagonal is a very important diagonal. And if we added the elements in any given square matrix, we call that the trace. So, for example, this generic 2 by 2 matrix, the trace would be A plus D. Now, the determinant of a 2 by 2 matrix has a very easy formula, but the larger matrices, we will have to use our calculators in order to calculate the determinants. And once you see where all your matrix menus are in learning the basic operations and how to put a matrix into your calculator, you will be able to see these commands. So DET is a command in the matrix menu, and you would just take the DET of a matrix you created in order for you to find the determinant of something larger than a 2 by 2. It is much faster to find the determinant of a 2 by 2 by simply using this formula, which it looks just like a crossover. So you do A times D, come back up, minus B times C. So I think of it as an X. Now, for example, let's find the trace and the determinant of the following 2 by 2. Oh, I just dropped my iPad pencil. Hold on. Oh, got it. So our trace is adding. So if we look at this diagonal and we add the elements, our trace is 3 plus 6, which is 9. Now, we have no idea what that means right now. We will work on interpreting, but right now we're just working on the basics so that when we get to the section where we're interpreting, we are comfortable with how to find these numbers. And then the determinant is going to be, again, AD minus BC in this generic matrix. Somehow my C didn't get written. A, B, C, D. Again, it is this type motion where we multiply and then subtract. So you're multiplying for the determinant of A, you are multiplying 3 times 6 minus -4 times 2. So that gives us 18 plus a positive. So we have plus 8. And that gives us 26 as the determinant. Again, right now we are focused on the computation part. We will focus on interpreting these in the next section. Okay, make a note that you already learned determinants in a previous section when you were using that matrix. So we already started seeing some sort of matrices in differential equations. That Wronskian matrix was a way of calculating the determinant. So now there is plenty of ways that we can calculate a 3 by 3. We can do the determinant out by hand, but again, it's not necessary because we're going to be using our calculators to find the eigenvalues without doing it out by hand. So I would highly recommend that you just use your calculator for this. And again, in an 89, it's fairly simple to do. You would, let's see, you would, hold on, you know what, I'm just going to stick to my original thing and I'm just going to post some videos on that for you guys in the class, in the content folder. Let's talk about a system of algebraic equations, because when we are typically using matrices, they are representing usually a system. Not always, but the ones that are representing a system of linear equations and in multiple dimensions, it doesn't need to be in just 2 dimensions, although this example is only in 2 dimensions. You can see that there's an x1 and x2. It's the same thing as using an x and y. When we when a matrix represents a system, we call it an augmented matrix, so that we know that everything to the left of the last column will be coefficients of variables, and the last column will always be the result column. Okay, it is systems of this type that we'll be interested in when we are using n linear equations and n unknowns. So again, multi-dimensions and multi-equations. So if we consider this system, we can put this system into matrix form by reading off the coefficients: 2, 1, 2, 1, negative 1, 1, negative 1, 1. The solution vector is what we're trying to find. What values of x, x1, x2, the variables, will satisfy this equation. So essentially, when you guys were in algebra class, you would have used elimination, substitution, or graphing to solve this to find x1 and x2. And we have other methods in the matrices world that would solve the system for us, called the reduced row echelon form, or using a Gauss-Jordan method. Again, that type of advanced matrix operation would be taught in a class like linear algebra. Now, B is the column on the other side of the equal sign, so that's that 1, 3. And when we put it together, we have ourselves an augmented matrix. So you would see this as a 2 by 3 matrix, 2, 1, negative 1, 1, and then 1, 3 would be the final column that would come here when we put it together. We will need to use one of the major theorems in linear algebra. It states that the system AX equals B has either one solution, no solutions, or infinitely many solutions. And that's the same when we were learning this in elementary algebra or intermediate algebra. We learned that linear equations either intersect all in one exact spot, giving you a one solution, or they're all parallel and they never intersect, giving us no solutions, or they're all the same line and therefore intersect in infinitely many places. Everywhere that the line, all the points, infinitely points on the line. Furthermore, if A is a square matrix, then there is exactly one unique solution if and only if the determinant is not equal to 0, which we already started analyzing when we were working with that Wronskian matrix. We can also write systems of differential equations in matrix form. First, we must define what it means to take the derivative of a vector function. So if x of t is equal to and represents a matrix, then we define the derivative, taking the derivative of each element in the matrix. Okay, so we would take the derivative of each one separately. So if we were to write this differential system, equation system in matrix form, let's do that together. Okay, so taking a look at this, we first want to build the coefficient matrix. So again, we would be, oh, that's the other side of the equal sign. So this is the vector B, and this is going to make up the coefficient matrix A. So our coefficient matrix is 2, 1, negative 1, 1. While our solution vector X is generic with the variables that are unknown. And our B vector is, oh, wait, yeah. No, we don't need the B vector because these are differential equations. I'm sorry. Take the B out of there. Don't need that. Got a little carried away there. Okay, so we have our coefficient matrix. We have our solution vector X. Now, AX looks as follows. So we have 2x1, negative x2, x1, and positive x2. And we have our derivative vector is going to be the derivative of the first term and the derivative of the second term. So the differential equation system becomes x prime is equal to ax. And we will do more with that in solving and you seeing how to apply that stuff in our future sections. Okay, so again, I will post YouTube videos about how to use the calculator to create matrices and do basic operations. So look out for those along with this lecture.